Hey everyone, today we're going to be starting Unit 8, which is a unit on applied trigonometry. 8.1, we're focusing on right triangle trigonometry and how we can use it to solve some applied problems. Okay, so we have, in the last couple units, we've been taking a little bit of a circular approach to our trigonometry. Where our angle theta is being created from an initial ray on the positive x-axis and then a terminal ray that passes through some point P on a circle, right? And that point P would have coordinates of x and y to it. What that gives us is an associated right triangle where the side lengths are considered x and y, again the coordinates of point P, and then r is the hypotenuse, is like the radius of the circle. Okay, well, we're going to throw out the circle now and look at this strictly from a triangular approach, a right triangular approach. And I'm going to say that if this is my angle theta in the picture in the top right here, then this would be the side that is opposite of it. This would be the side that's adjacent to it. And then, of course, we have our hypotenuse of the right triangle, which is the longest side, and it's across from the right angle. Okay? So think about how that would change our trig functions definitions from this approach. Normally, we would say that sine of angle theta is defined to be y over r, right? Well, in this case, think of y, it's like the length of the opposite side of this triangle, or the opposite side of this angle. So I'm going to replace y in the ratio with opposite, and then r is like the length of the hypotenuse. Okay. Cosine we've been defining as x over r. Well, in this case, x is like the length of the adjacent side to the angle theta. So I'm going to say that x can be replaced with the length of the adjacent side, and then again over r, which can now be thought of as the length of the hypotenuse. Tangent we've always defined as y over x. That can now be thought of as the opposite side length to angle theta divided by the adjacent side length. All right, and this approach, I'm sure many of you have heard of the acronym SOHCAHTOA that can be used to remember these definitions. So that word looks like this. And we're going to break it up into 3 syllables. So starting with the first syllable, S can be thought of as sine. And then O would just stand for your opposite side length. H would stand for your hypotenuse. So that's just telling us that sine is equivalent to the opposite side length divided by the hypotenuse. In the second syllable of this acronym, you've got C for cosine. A would be for adjacent, H for hypotenuse. So that's, again, just saying cosine is defined to be the adjacent side length divided by the hypotenuse side length. And then the third syllable, T stands for tangent, and O opposite, A adjacent, right? So tangent is the opposite side length divided by the adjacent side length. Real easy way to help remember each one of these definitions. And then, of course, our reciprocals are still at play for secant, cosecant, and cotangent, right? Okay, so now that we're taking this right triangle approach, I think it gives us a good opportunity to really conceptually understand what these ratios represent. Okay, so when I say that sine of the angle theta is equal to the opposite side length of theta divided by the hypotenuse length, understand that ratio, it's giving you a percentage of how long the opposite side should be in comparison to the hypotenuse. So I'm going to pull up this illustration. I think this is going to be a really good visual to help you conceptualize, what these trig ratios represent. Okay, so you can see we're working with an acute angle alpha here of 50 degrees. And notice we're taking this right triangle approach where we have this green leg that's opposite of alpha. We have this purple leg that's adjacent to alpha. And then, of course, we have the black side of the triangle, which is your hypotenuse, right? So we know that sine is, again, defined as the length of the opposite leg or the opposite side of the triangle to this angle divided by the hypotenuse, right? Well, when you're dividing those two numbers, you're coming up with a ratio that ultimately gives you the percentage that leg should be in comparison to the hypotenuse. So you can see sine of 50 degrees is approximately 0.77 units, okay, which means in any right triangle with a 50-degree angle, the leg that is opposite it should be 77% as long as the length of the hypotenuse, okay? For cosine, we know that's a measure of the length of the adjacent side length with the hypotenuse. So cosine of 50 degrees is 0.64, 64 hundredths. So we're saying that this adjacent side length to a 50-degree angle should be 64% as long as the hypotenuse. All right, and then think about tangent. Tangent's a measure of the opposite side length in comparison to the adjacent side length. Okay, so in a 50-degree angle within a right triangle, tangent of 50 degrees is 1.19, which means the length of the leg that's opposite that angle should be 119% as long as the adjacent leg's length. Okay, so hopefully that just gives you a real good understanding of what we are doing when we're coming up with these values for our trig functions. Okay. All right, let's get into an example. So before I solve this problem, let's just make sure we understand some common triangle notation. We typically will represent our vertices of the triangle as capital letters. So you can see I have capital letters A, B, and C. And then notice that the sides of the triangle that are opposite each one of those vertices are designated with a lowercase letter, right? So like this is lowercase a because it's opposite the vertex of A right there, capital letter A. Okay, and that's just very common notation that you'll see being used. All right, so we want to find the value of A, so the length of A here, if C is 6 units and the measure of angle A is 25 degrees. So again, we're being told this is 6 and right here is 25 degrees. Think about if we're trying to solve for the value of A, think about the givens and what trig ratio I can use here. This side length A is opposite 25 degrees, right? And then C is the hypotenuse. So this is an opportunity for me to use the sine function, which is, again, defined to be opposite side length divided by the hypotenuse. So I can say that sine of this 25-degree angle should equal A divided by 6, opposite side length over hypotenuse. And now to solve for A, I just need to multiply both sides by 6. Get those to wipe out, and then this would be calculator work. Make sure your calculator's in degree mode. Let me type it in here. 6 times sine of 25 is 2.54 units approximately. Okay. All right, next example. This time we're trying to find an angle theta here. And notice the lengths of the sides of the triangle that we're given. They're the two legs, right? We don't know the length of the hypotenuse. We could use Pythagorean theorem here if we really wanted to find the length of the hypotenuse, but I don't think it's necessary because we can use a tangent function. I can say that tangent of my angle theta should equal the length of the opposite side of angle theta divided by the length of the adjacent side. Now we could reduce that. We could say tangent of theta is equal to 5/2. And to solve for theta, we're going to need an inverse function here. And once again, let's be in degrees. So I'll take inverse tangent of 5/2. And that's 68.20 degrees. So 68.2 degrees. Okay. All right, now let's do a little applied problem. This one's, kind of for fun. Ashley's watching her friend Chris fly by in a hot air balloon. The angle of elevation from Ashley to the balloon is 72 degrees. When we say angle of elevation, that's meaning if Ashley's standing on the ground, the angle between the ground and when she looks up at Chris is 72 degrees. That's your angle of elevation. It says the distance from Ashley to the balloon is 200 feet. We want to know if Chris jumps from the balloon, how far will he fall, right? So think about, we're trying to find H here in the picture. Notice there's a right triangle associated with this. We're considering he's going to fall straight down to where it would create a right triangle. And that side length would be opposite the 72 degree angle of elevation we know. And then the 200 feet would represent the hypotenuse of that triangle. So this is another opportunity to use the sine function. I can take sine of the 72 degree angle and equal it to the opposite side length, which is unknown right now, divided by the length of the hypotenuse. Okay, multiply both sides by 200. Those wipe out. And let's see what we get. 200 times sine of 72 degrees would be 190.2. And don't forget units here, that's feet in this case. All right, so Chris is going to fall a long way to get down to Ashley. That's probably going to hurt. Hope he loves her. Okay. Last example here. So this is going to bring in the idea of co-functions. All right. So take the picture that's to the left there and notice I'm trying to find first sine of angle B. This is angle B right here. Based on the way this picture is labeled, I would say that sine of angle B is equal to side length B divided by the length of the hypotenuse, B over C. I also now want to find cosine of angle A, which is right here. Now cosine is defined to be the adjacent side length to the angle. So in this case, for angle A, that would be side length B divided by the hypotenuse. All right, so what we want to notice here is that we're getting the same ratio for both sine of angle B and cosine of angle A, okay? And that is because sine and cosine are co-functions of each other. All right, now notice angle A and angle B, they have to be complementary angles, right? We're in a right triangle here. We have a right angle, of course, at C. That means that angle A, the measure of angle A added with the measure of angle B has to be 90 degrees, right? So that takes us to a complementary angle theorem. It says cofunctions of complementary angles are always equal, right? Sine of angle B here is equivalent to cosine of angle A. And this is why if you're calling the first function sine of angle B, we have cosine of angle A. They are cofunctions, okay? This would be the same for secant and cosecant, right? Secant and cosecant would be both equivalent to C over B here for measures of angle A and B. And then we have tangent and cotangent. They would be equivalent to each other, okay? All right, so by this theorem, we could say tangent of 35 degrees would be equivalent to its cofunction cotangent of 90 degrees minus 35, or cotangent of 55 degrees. Okay. Applying the same theorem, if I have sine of 60 degrees minus cosine of 60 degrees, there's a couple ways you could look at it. Sine and cosine are functions, cofunctions of each other, and I'm noticing the angles that I'm working with, those are complementary, right? 60 degrees and 30. So one way of looking at this is that cosine of 30 degrees is also sine of 60. And of course, sine of 60 subtracted by itself then would be 0. Okay.